There is another test that's useful in determining whether a series is absolutely convergent. It's called the ratio test. So what we will do is we will set up a limit of a ratio. In the numerator, we'll put the next term. In the denominator, we'll put our term. When we get limit L, we'll determine if it is less than 1, greater than 1, or equal to 1. One of these three cases will occur. If the limit is less than 1, then the series is absolutely convergent, therefore convergent. If the limit is greater than 1, or the limit equals infinity, then the series is divergent. If the limit equals 1, the ratio test is inconclusive. By the way, go to the ratio test if we have nth terms that contain an exponential, or if there is a factorial in the nth term. We'll begin with number 18 as an example. So in number 18, I'm going to set up a limit of a ratio. Now it's the absolute value of that ratio. The negative 1 to the n minus 1 component is not necessary because we're taking the absolute value, so the result will be positive either way. In the numerator of our ratio, we want to put the n plus 1 term in that spot. So we'll have 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 to the third power. In the denominator, we'll just copy down our nth term, 3 to the n over 2 to the n cubed. I find it easier to write it as the numerator times the reciprocal of the denominator. So I'm going to rewrite absolute value. Now 3 to the n plus 1 is in the numerator. 3 to the n plus 1 is the same as 3 to the n times 3 to the first. So this is the moment at which I will switch that exponent over. And then in the denominator, I would have 2 to the n times 2 to the first. So I broke up 2 to the n plus 1 this way. And then I have n plus 1 to the third power. So that was the top fraction. The bottom fraction will get flipped because we're multiplying by the reciprocal. Therefore, the fraction I'll write down is 2 to the n times n to the third over 3 to the n. As you can see, I can cancel some of the terms. 3 to the n can cancel. 2 to the n can cancel. That leaves us with 3n cubed on the top and 2 times the quantity n plus 1 cubed on the bottom. I'm going to remove the 3 halves from that fraction. Let's pull 3 halves out in front times the limit, and the numerator has an n cubed in it. The denominator has n plus 1 quantity cubed in it. To evaluate that limit, I'm going to divide top and bottom by n to the third. So we still have 3 halves out in front times the limit, and the numerator is going to be 1 because I divided the numerator by n cubed. The denominator, it's going to be n plus 1 divided by n to the third because I'm dividing top and bottom by n to the third. So in that denominator, I have 1 plus 1 over n to the third. Now when I evaluate this limit, I will get 1 over 1 plus 0, which is just 1 over 1. So this product equals 3 halves. Notice how 3 halves is greater than 1. If the limit is greater than 1, then the series is divergent. Number 20. Right away I notice there's a factorial in our nth term. I'm going to set up the ratio test. They're actually using k instead of n in number. We'll set up our limit as k approaches infinity, and the numerator is going to be the k plus 1 term. Replace k with k plus 1 and then leave the factorial there. The denominator is 1 over k factorial. I want to rewrite that fraction. So the fraction on top is 1 over k plus 1 factorial. Now, I need to break that factorial down a little bit. As you recall, when you have a factorial, let's say 4 factorial, you can break it down into 4 times 3 times 2 times 1. But in this situation where you have a variable there, your breakdown has to be this. Take the n, that is obviously the first factor in this product. Then the next factor is 1 less than that. So it would be n minus 1 would be the next factor. This could go on for a while. N minus 2 times n minus 3 times n minus 4 and so on until it ends. We don't know where it ends when we have a variable. So we break it down as far as we need it, and then we place the factorial at the end. So I'm going to rewrite this k plus 1 factorial in the same way. Take away this factorial symbol for the moment. Now, the first term is k plus 1, and then the next term is 1 less than that. So k plus 1 minus 1 is just k. That's as far as I actually need it to go, so I'm going to write the factorial after that factor. Now I'm going to multiply by the reciprocal of the other fraction, so I'll have k factorial over 1. Now you could see why we broke that down. The k factorial in the numerator is going to cancel with the k factorial in the denominator and just leave a k plus 1 behind. So this is the limit as k approaches infinity of 1 over k plus 1. Of course, this limit is actually equal to 0, and 0 is less than 1. When your limit is less than 1, then the series is absolutely convergent. Would you please try our last example on your own? So pause the video, try this example, and then turn the video back on to check your answer. As soon as I see the factorial, I think about the ratio test. I'll set up the limit as n goes to infinity. The n plus 1 term goes on top. The nth term goes on the bottom of that ratio. I like to rewrite the fractions side by side. So leave the top fraction the way it is. When I write the top fraction, I'm going to break it down. 2 to the n plus 1 is the same as 2 to the n times 2 to the first. The factorial on the bottom, I'm going to break it down one step. So I will write n plus 1, and then the term that is 1 less than n plus 1 is n, and I'll copy the factorial after that. The denominator is going to get flipped, so n factorial goes to the numerator, and 2 to the n is in the denominator. You can cancel 2 to the n, and you can cancel n factorial. Now I'm left with 2 in the numerator. You can bring 2 out in front of the limit. That leaves behind 1 over n plus 1. The limit as n goes to infinity of 1 over n plus 1 is 0, and 2 times 0 is 0, which is less than 1. Remember, with the ratio test, we're always comparing whether our result is less than 1, greater than 1, or equal to 1. This time it's less than 1, so that means the series is absolutely convergent.